Hey guys, welcome back. Turned uh I turned the tape on. How are my mega minds doing today? How are y'all? Not bad for a Monday. You should be I'm only partly joking when I say mega minds. You should be feeling your power growing each day, right? Um as you're learning more calculus, getting closer to being able to take over the world, which is your destiny, okay, as a calculus 3 student. So don't forget that. Um, and also don't forget that calculus is a very valuable skill that you can sell. Okay. And the reason I say that is one way that you can sell your skill is by becoming a tutor. So if you ever thought that you might be a tutor, it's a really good experience for lots of things because you have to interact with people and deal with people. And so you learn a lot about, well, you learn a lot about how other people are thinking about math and other things when you become a tutor. One way you can do that is by applying to be a supplemental instructor. Have y'all had supplemental instructors in class before? So they're kind of like class tutors. So here in Calculus 3, you'd be a good candidate to be a supplemental instructor for a lower level math course, particularly calculus. So you may consider doing that. You can apply in South 405. That's the SI Tutoring Center, if it's still there. So I'm sure it is though, South 405. So you can go by in the one main building. So you can go by there sometime and ask about applying if you're maybe interested in doing that. Okay. Um, so they'll try to work around your schedule and so forth, right, to make it possible for you. Um, okay, so I wanted to make sure I mentioned that before the end of the semester. All right, so we have this homework on partial derivatives that's due tonight. So I had shifted that back, and I know I have maybe one question from partial derivatives, and then one question that occurred to me also when I was looking through those questions, and then we're going to go back and finish up on our notes on directional derivatives, and in particular, finish the very first example or the first example from those notes because I added to the notes. There's something that I had left off of the notes for some reason. I don't know why, and then I'd subsequently forgotten about it, and then we rediscovered it last time as we were going through the first example from that directional no from one of the examples from that directional derivatives notes, and then that uh, caused me to think about what I was forgetting. So I stumbled a little bit at the end of lecture last time. So I went back and fixed that. And So we'll finish up that example that we sort of left hanging last time. And then we're going to go on and talk about tangent planes, which I think you're going to find easy to understand. Okay. All right. So anyway, so from this homework from partial derivatives, Fatin, you had a question. And then there was one question that I wanted to mention that's not really um, as difficult as it appears when you first read the question. And then if other people have questions, you can ask. So this is all about calculating partial derivatives. But there's one question, this one, okay? So it's really not difficult, but it looks intimidating because it says, use a computer algebra system like Wolfram, for instance, is an example of a computer algebra system, to find the first and second partial derivatives of the function. And then it says, determine whether there exist values of x and y such that the first partial derivative with respect to x, right, is 0, and the second partial derivative with respect to y is 0 simultaneously. Okay. You don't have to use a computer algebra system. You can work on finding the first and second partial derivatives there just by hand, and they don't even ask that to fill that in, right? So um So you can just do your best in finding those first and second partial derivatives. But the first derivatives are easy to calculate in any case. So here's our function, what, x secant y, right? So let me find some blank paper here in the note so we can write that down. I think they were just trying to give you practice with using computer algebra systems, but we really haven't. I mean, we've demonstrated that in class occasionally, but we really haven't really focused on that in class. But I don't think you need a computer algebra system in order to do this problem, is the point I'm trying to make, and that's why I think I assigned it. So let's see, oh, fooey, did I close my, terrible about that. Let's try. All right, so let's write down that function. So it's just what, f of x, y is equal to x secant y. And so the first partial derivative with respect to x, right, is so easy, correct? Because the secant y is going to be a constant, right? So you really just have here a constant times x when you're differentiating with respect to x. So anytime you just have a constant times x, right, when you differentiate that, you're just going to get the constant. So the partial derivative with respect to x is just secant y, right? And then if you want to differentiate that again, right, with respect to x, for example, that's so easy because now this is just a constant you're differentiating, right? So you're just going to get 0, right? If you take the derivative with respect to y, on the other hand, okay, maybe that's a little bit more challenging, right? Because here, x is playing the role of the constant, right? So what you really have is a constant here times secant of y, right? And so you just have to remember what's the derivative of secant, correct? And what is that? I think it's secant tangent, is that right? So it's secant y times tangent of y. And now this is going to be a little bit more challenging to find the second partial derivative with respect to y, right? Because now you're differentiating this constant times secant y times tangent of y. And so you're going to have to remember the product rule, okay, in order to differentiate this a second time with respect to y, correct? So you have to remember to use the product rule here. And then you have to also remember, oh, what's the derivative of secant? What's the derivative of tangent? Well, we know the derivative of tangent, of secant, right? That's secant tangent. And what's the derivative of tangent? Secant squared, right? So you get a little bit of review of some of your more exotic derivatives of trig functions, correct? So I'm not going to write that down fully, but you can continue that process here to find the second partial derivative spectrum. Remember, x is a constant, right? So it's going to go along for the ride when you're taking the derivative, but it's not going to really contribute anything to the derivative, correct? Now, the second question was, okay, so is there are there values for x and y, right, where both of these first partial derivatives are 0 simultaneously? So can you find values for x and y that will make secant y 0 and also x secant y tangent y 0 at the same time, correct? So we want to solve these two equations simultaneously, if possible. But that's not possible because secant y is not going to be 0 ever, right? Okay, because remember, secant y is the same as 1 over the cosine of y, correct? And that is not going to be 0, right? Because the numerator is never 0 in that fraction. It's going to be undefined in several places, of course, but it's not going to be 0. So that means you can't even find a solution to the first equation, much less simultaneous solutions to both equations. So the answer there that you want to put into the system is, what does it tell us there? D and E does not exist. All right, so the answer there is just D. Okay. All right, so so you don't need a computer algebra system your brain is a plenty good computer algebra system for that problem. All right, Fatin. So what was the problem, though, that was troubling you? I think it's the same problem, isn't it? But just in a little bit different setting. Aren't you also setting the partial derivatives to 0? Which one is that one? Oh, this one. Okay. All right. So do you have the same? We can adjust. Is your problem the same? Do you have it written down? Is it the same coefficients? Oh, let's write down your problem then. Same thing. The 8 is a minus 11, so it's 2x cubed minus 11xy plus y cubed. Okay, right. So, that's how it generates different problems, right? Is often by adjusting coefficients. All right, so we'll write down your version of the problem. Just see if we can help you. And I think one thing that is maybe difficult here, though, is typing in the apparently there's 2 solutions here, right? So typing in the solutions might be challenging. But they want exact solutions, I think, because they're not telling us to give us decimal equivalents. So or to round off, right? So you do have to be careful about how you're going to type in the answers here. All right. So let's see, Fatin. So I'm not going to be able to type in the answers because I'm solving Fatin's version of the problem. But let's see if we can maybe write the answers down in exact form in a way that we think we can enter it into the computer. So what's the function? Minus 11 something. 11xy plus y cubed. All right. So we're going to take the partial derivatives, right? And then set those to 0 and see if we can discover simultaneous solution there. Okay, that's probably the hard part. The partial derivative is probably the easy part here, right? So when we differentiate with respect to x, well, that term is easy now to differentiate with respect to x, right? That looks like a calculus 1 problem. So the derivative there is going to be 6x squared, right? Bring the 3 down. And then here, when we differentiate with respect to x, well, also easy, right? Because this is really just a constant minus 11y times x to the first power. So the derivative of that is just going to be the constant, which is minus 11y. So the x will just disappear. And what's the derivative of that term with respect to x? 0, right? Okay, that's just going to be a constant. Yay, so that's pretty easy, right? And remember, we're going to set that to 0. And then now let's take the partial with respect to y. So let's see, is that in each half? Well, this is 0, right? And now here we get minus 11x. And then that third term is easy to differentiate, right? That's 3y squared, okay? And so we get minus 11x plus 3y squared. And now we want to see if we can solve those 2 equations, these 2 equations simultaneously, right? So usually the way you will solve simultaneous equations, right, unless there's something that makes the equations easy to solve, like in that first problem that I showed, right, is you'll, one technique, right, is to solve one of the equations for one of the unknowns, whichever is easiest, right, and then substitute into the second equation, okay, and see what happens in that case. I think this first equation would be easy to solve for y, correct? Because we just have y in the first power. Not easy to solve for x because we have x squared. That makes it quadratic x, which is going to be harder to solve. Second equation also not easy to solve for y, right? But easy to solve for x because x. So take your choice there, right? Of what you want to do. Do you have any suggestions? I didn't try this beforehand, so I don't know.
So one in terms of x, y.
So you're going to do what now?
Solve for
the y in the first equation. Okay. So so we can shift the 11y over, right? To the right-hand side. So that gives us positive 11y, and then I guess divide by 11, right? So you would have y is equal to 6x squared over 11. And now, oops, now we have to substitute that right in here. Ooh, ugly, right? Okay, but that's life. So now we have minus 11x plus 3 times all of this, unfortunately squared, right? Is equal to 0. Okay, I see. So the solutions here are really going to be ugly, right? Okay, not difficult necessarily, but not pretty to look at, right? So we have minus 11x plus. Let's see, when you square inside the parentheses, what is that? 36x to the fourth over 121. And I forgot the 3, right, which is multiplied in there, okay, is equal to 0. I don't think the 3 helps helps reduce the 121, right? Because 121 is 11 squared, so 3 doesn't go into that, right? So we get 3 times 36, which is what, 108 x to the fourth power over 121 minus 11x. I'm just rearranging the terms there a little bit, equal to 0. Okay, so now we're left with trying to solve. Now we're left with trying to solve that equation. All right, not quite quadratic, but it is a polynomial equation, right? It's a polynomial equation. So so we have some chance there at solving that. What do y'all?
Took out X that.
Took out the common x factor, right? So we have x times 108x to the fourth over 121 minus 11, right? 108, oh, x to the third, yeah, okay. Good thing you said that, or we would have ended up with the wrong power there, right? So that would have messed things up. Yeah, separate the 2, right? See, now you have a product that equals 0, right? So you know x is equal to 0. Yay! So there's one possible solution. That's probably maybe the smaller x value, right? Okay, and then or we have all of this equal to 0, and that's the one now that we have to think about, right? So this minus 11 equal 0, right? Shift the 11. I'll buy that. So this is equal to 11. Multiply both sides by 121. Okay, all right. That wasn't what I thought to do there, but that's fine. All right, so we have 108x cubed equals to 11 times 121, better known as 11 cubed, and now divide by 108. So we have x cubed equals to 11 cubed, because 121 was 11 squared, right, over 108. I like writing it as 11 cubed because we're getting ready to do what here? Take the cube root, right? So we have x is equal to, and you don't have to write plus or minus because numbers only have one cube root, right? They have 2 square roots, but they only have 1 cube root, so we don't have to write plus or minus the cube root here, right? So we have the cube root of 11 cubed over 108, and now I have to figure out how to reduce that cube root as much as possible by hand. Well, part of that's easy, right? Because you're taking the cube root of 11 cubed, that's 11, so you end up with 11 over the cube root of 108. And now we need to think about factoring 108. So how does 108 factor? Because I want to see if I can factor it into perfect cubes, right? So how can you reduce 108, or how can you factor 108?
Same as cube root 7.
Yeah, it's 4 times 27, right? Is 108. Of course, you can write 108 as a product in lots of ways, right? So you may take a little trial and error here to see how to write it correctly. But it is 4 times 27, and that's useful because 27 is a perfect cube, right? It's 27 here, right? 27 is a perfect cube. Its cube root is 3. So you end up with 11 over the cube, I'm sorry, 3 times the cube root of 4. Now, 4 is not a perfect cube, right? It's a perfect square, but not a perfect cube. So you cannot reduce that. That's it. So there is, by hand, the reduced version of that second solution, right? Now, of course, you have to find the y coordinates also as well, right? So now you will have to take your value for x, right? And you're going to have to plug it in maybe right here, correct? To get the corresponding value for y, right? Because remember, we discovered that y was somewhere in the process of solving these equations simultaneously, right? We discovered that y was 6x squared over 11. So now we can use this equation to find the matching y coordinate. What's the matching y coordinate for 0, though? Because we had x equals 0. Is that 0? Because if you plug 0 in for x here, you'll get 0. So that's easy. That one you probably got right. Is that right, 15? Okay, all right. And then now for the other one, wow, what's that going to be? Well, I know the x coordinate was what, 11 over 3 cube roots of 4. And now what's that y coordinate going to be? Let's see. Wow, 6, and then times what is it? 11 over 3 cube roots of 4 squared, and then all of that divided by 11. Wow, ugly, right? Can we simplify that some? Not too much. Try square this, right? So what will that give us when we try squaring that quantity inside the parentheses there? Yeah, 121, also known as 11 squared. I'm going to leave it written as 11 squared over what? 9. You can also write that as 3 squared. And then what happens to this cube root when you square it? So you're squaring these things, right? So you can multiply this times itself. So you get the cube root of what? 4 squared, which is 16. Okay. And then all of this is divided by, still by this 11, right? So what happens to that? How do we try to have a complex fraction, right? So that's really what happens to this 11? I think it will divide out this one, right? This 11 will divide out this one. See, dividing by 11 is the same as multiplying by 111. So you're multiplying this fraction by 111, which means one of these 11s divide out, right? So that makes things nicer. That's easier to look at. So we can get rid of the 11, one of the 11s there. So I have just 6 times 11 over 9. And then I have the cube root of 16. But 16 is what? That is 2 to the 4th power. But 2 to the 4th power is 2 cubed times 2, right? 8 times 2 is 16. And I like it writing it like this because now I'm extracting cube of 6. So you can
that out, you're gonna have 2 times 9, which is 18. But 6 will divide into, right? So you end up here with 11 over 3, I think, times just the cube root of 2. That doesn't look all that bad after everything was said and done. Did I go too fast there? Or did I do it wrong?
66.
What now?
66 and
66 and oh, did I forget the? Oh no.
wait, no, you divide it.
Yeah, because I pulled the 2 out, so I had 18. 6 goes into 18 times, right? Yeah, and then the 11 is left with just left. The middle. So as the second coordinate there. Woo. So 11 over 3 times the cube root of 2. Well, try that, Fatine. The answer was something like that. I did see the correct answer for your version of the problem, something like this, but I can't remember exactly what it is. So if I messed it up, well, you'll have to fix my mistake. Okay, that's all. Okay, so hopefully I won't give you one like that one on the test, although I may give you a question like this, where it says, where are the 2 first partial? It's simultaneously 0. That becomes important. I think we've already seen why, because that's going to tell us on surfaces where we are, where a critical point is, where we're likely to be at a maximum or at a minimum. So we're at a point or a value. Okay. All right. Okay. I'm scared to ask for other questions now. Are there other questions there from partial derivatives? Did y'all understand the last question, which is about marginal cost? That's an economics question, but so this is just so easy. Take first partial. It's in economics. First derivatives of cost functions are called. Those are called the marginal cost function. Finding the marginal cost function back to epsilon. So that's just really trying to understand and try to do that problem. But what marginal cost tells you is exactly what's described in this sentence, and this is why one of the reasons why economists are interested in this, right? So it says when additional production is required, the model of Stowe results in which model of Stowe results in cost increasing at a higher rate. Remember, these partial derivatives are like slopes, right? Okay, and so the slope that turns out the largest there is going to be cost that's increasing at a higher rate. So first derivatives, which is what explain. That's the classical notation, right? Sure. A partial derivative, right? With respect to y, and partial derivative with respect to x. Okay. Let's now the famous saying from economics is when marginal cost is the same as marginal revenue, that's where profit is greatest. When marginal cost is the same as marginal revenue. So marginal revenue means the derivative of the revenue function. All right, let's go back now up in these notes and let's finish this first example. Well, we had really finished it last time, and we had finished it correctly, but I just wanted to remind us there of what we had done, right? So remember, we had this plate, right, that was on the surface of the spaceship, and it was heating up, and this function well, I covered it up, but that function that tells you the temperature of the temperature of the plate, right? Various points on the surface of the plate. We superimpose an XY axis, right, on that flat plate. This is the graph of the temperature. And the plate is not low, right? The plate itself is flat, like XY axis, but this surface, right, shows us the temperature at various places on the surface, right? We had already discovered, right, that at the contour map, this temperature function, that the temperature was highest right there in the center of the plate. And there are the partial derivatives of that temperature function. We had computed those. There's the temperature function that we were using. And actually, the question that we wanted to answer was, what's the gradient, right, at of the temperature at this particular point on the surface? Okay? So remember, the gradient is a vector. It's a two-dimensional vector. And you can sort of think of it as telling you what's the compass direction on a move plate, right? What's the direction you want to move on that plate? Where the temperature on the plate is going to be increasing the fastest. Okay, so what direction the fastest in the temperature this particular, right? And so we computed we calculated the gradient vector somewhere here. So somewhere here, calculations. I think here it is. Right. There's the gradient vector from that particular point on the XY plane. Remember, the circles here are just the level curves, right? This is the contour map, that temperature function, right? So here's a picture there that gradient vector. So apparently, from this particular location on the plate, right? If you this direction, the temperature is increasing fastest from this particular. Now, and then the second question, the one that sort of got, one that I stumbled on there is, but what is the rate of increase in the temperature? We know we want to go in this direction, right? But what is the rate of increase in the temperature in this direction from this? So what we're asking for here is a directional derivative, right? The rate of increase in this function from this particular, or the slope of this surface in this particular direction, but that happened to be gradient direction. That was the direction where the temperature was increasing the fastest, and we calculated that, and we did the calculations correctly. The slope of this surface in gradient direction. But what I had forgotten, last time too, I don't know why I didn't include this in the notes, is this very useful theorem, okay, which tells you this. So we could have saved ourselves a lot of calculations in a class last time. So remember, the gradient tells you the direction of maximum in a function, okay, or direction you want to move, so that the surface is increasing or perhaps decreasing, is ascending or descending fastest. If you go in the direction of the gradient, you're going toward the maximum increase. If you go in the opposite direction from the gradient, so if you go in the gradient negative direction, going in the direction of fastest descent. Okay, so the gradient shows you how to ascend most quickly on the surface, and the negative of the gradient tells you just the opposite direction. Tells you how to descend most quickly on the surface, right? But gradient is a direction, right? It's a vector. It doesn't tell you what the rate of increase is, what the rate of ascending, what the rate of this case, in negative direction, what the rate of descent would, right? That's a slope. That's a derivative. And so we calculated last time the directional gradient. That's where we came out with 17.09. But there's a very easy theorem that we sort of rediscovered last time while we were doing those calculations. And that is just the magnitude of gradient is the slope of the surface in direction. Just calculate magnitude, that will tell what the derivative of the surface is, or the slope of the surface is in direction of. Or if you take the negative of that will tell you slope is in the fastest descent. Now, that result comes from a prior result that I also forgot to tell you, which is also useful, okay, but which provides you a little bit of a shortcut. But remember, you want to find a direction of the maximum slope, right? Or the direction of the direction of the maximum slope. That's the gradient. And then if you want to find the slope in that maximum direction, you just have to find magnitude. That tells you, see, that's perfect. So the gradient really tells you everything about how to ascend or descend in the steepest fashion on a surface. But this result comes from another result that I also forgot to tell you, which is also useful. So remember, in the prior notes, we had talked about computing directional derivatives, right? The derivatives in a particular direction. So if you want to find the derivative of a surface in the direction of some vector u, this is the formula that does that for you. But remember, u has to be a unit vector. So if u is a unit vector, you're going to find the slope, right? The derivative of the surface in the direction of that unit vector, just use this formula, right? So it's the first partial derivatives, and you have to know cosine and sine of the direction of the vector. Remember, the vector u is going to be a two-dimensional vector. Anything on xy plane, particular direction, that will be up or down surface, right? Function value. But okay, there's a nice shortcut now. If you know the gradient, if you have calculated the gradient, it also could directional without having to know these sines and cosines. All you do is take dot product of the gradient vector. So if you know the gradients, you can also easily now compute directional vectors as well. So gradients there are really, because they give us a shortcut in directional derivatives. So you can compute derivatives in other directions too, not just the gradient direction. Remember, the gradient direction is the direction of maximum ascent or descent, but the slope in other directions as well, if you know the gradient vector, just by using dot product. But don't forget, u has to be a so get that. So if someone says, "Oh, here's a gradient at a particular point on the surface, and I want to know what's the derivative in this other direction, pointing this way," well then, you just use this dot product. But remember, the direction they give you, they have to give you that direction as a unit vector. So if this is not a unit vector, you have to turn it. So I put those two things back in the notes. Those are maybe helpful short ones. All right, now let me show you. Let me show you now why this is true. So why is the maximum slope at a point on the surface of a function? Why is the maximum slope the same as the magnitude? Well, here's why. So you can find the maximum slope, right, by finding the directional derivative from the gradient, right? The directional derivative in the direction of the gradient will tell you what the maximum slope is, right? So compute the directional derivative in the direction of the gradient. So let your direction vector here be the gradient. But what do we know about this direction vector? It has to be what? What did I just say? It has to be normalized. So if you're going to use the gradient vector, you have to normalize it, right? Because the gradient vector may not be a vector. So that's what I did, right? Let's take the gradient vector and let's normalize it. So how do you normalize the gradient vector? Just divide it by its magnitude, right? So here's the gradient vector divided by its magnitude. Now, from that earlier theorem, it says, oh, well, if you want to compute directional derivative, just take the dot product of the gradient vector with your unit vector, right? Well, here's our unit vector. That's the vector in the same direction as the gradient. And we just take the dot product of that with the gradient itself. But what happens when you take, this is the same vector, right? So what happens when you take a vector and you take the dot product of itself? That turns out to be magnitude squared. So in the numerator here, you just get the magnitude squared divided by the magnitude. Magnitude just divides out with just the magnitude. So there's the magnitude. So a slope in the direction of the gradient is just the magnitude. And that has to be the maximum slope. So if you're asked a question, say on the sample test, oh, the sample test is posted, right? So if you're asking a question on the sample test, and this is on the sample test, oh, what's the maximum from this point on the surface? What's the maximum slope? What's the maximum ascent? What's the rate of maximum ascent? Just find the gradient and then just put magnitude. See how nice vectors are? There's so many nice results like this in calculus 3. It's one of the makes it. So many of them, they're hard. All right, so that's what I forgot. That's why I left it off the notes. All right, so I put those back into the notes. So remember those two theorems that they may come up in your homework, and they will certainly come up on the sample test, which is posted now. So if y'all didn't get that email, it's posted in the usual spot on the Blackboard page, right under sample test. But it's just the blank test. The answers are not there yet. They'll come later. All right, now the next question that we had asked that we want to finish here now, because this is a really nice problem, is and useful problem too, is we know that when this crack starts at this point on the surface, right, the crack is going to, according to physics of the situation, crack is forming on this plate. It's going to travel. The crack is going to, and it's going to travel in the direction of maximum temperature change. Okay? So remember, from this point, maximum temperature change is in this direction. This is the gradient. So it's in the direction of the gradient. So at first, from this point, the crack is going to start forming in this direction. But the crack doesn't keep forming along a straight line, right? Because as you change positions on the surface, you from this point to just a point that go to the left here, right? Gradient at another point is going to change. Okay, but the gradient will change continuously. So crack is not going to continue in a straight line. So our question is, what does that crack ultimately? What does that crack end up? So if you think of that crack as being a curve, what's the equation? Now remember, this curve is on the xy plane, right? Okay, because the plate is a flat plate, right? But the curve is going to travel in the direction of these constantly shifting gradient vectors. So we were just speculating last time that eventually, right, we're thinking, it's kind of our intuitive thought is eventually that crack is going to get to the hottest point, right? Which is at the center of the plate. We can see that from the graph of the function, right? So we think eventually this crack will move here, but it doesn't start in that direction, right? The crack initially is going this way, according to the gradient vector. So that crack has to curve, right? So that means these gradient vectors have to start shifting direction, correct? Because they have to start nudging that crack toward the center of the plate, which is where the temperature is the highest. So we'd like to know what is, that's a curve, okay? So what is the equation that, see right there, kind of, by the way, making up that curve on the head curve looks like. Could be also, liquid. Doesn't feel like it, liquid, no, but it could be. So I'm just speculating there when I'm drawing that curve. But we don't have to speculate about exactly what is that curve that describes that crack surface. Okay, that's right. Now, here's the key thing to observe. Well, there are a few key things to observe. Look, this is a curve in the xy plane. So when you write down the equation for this curve, it's just in the variables x and y, right? Z is not involved. This curve exists on xy plane. So this is not really a three-dimensional problem, right? But now, the other thing to notice here is that, look, that gradient vector, right, is parallel at every point on that curve. The gradient vector is parallel to the curve, right? See, the gradient vector is kind of like a tangent line for that. That's the clue that. So that is a tangent to that curve. Think of that vector as being a line starting from particular that vector is tangent. So that means if you can think of the vector as being the slope, right? If you can think of the gradient vector as being the slope, then you know the slope of this curve is the same as slope. Right now, let's see if we know what the slope of the gradient vector is at an arbitrary point. So let's pick an arbitrary point on this curve, not necessarily the one we started with, right? Okay, and so if you draw the gradient vector from this point, we said it's kind of like the tangent line to the curve, right? So I'm thinking the gradient vector at this point looks something like this, correct? And let's just call this an arbitrary point xy. So I'm not going to specify the exact coordinates for that point xy. Let's just call it xy. So first, what is the gradient vector going to be at xy? I'm not going to fill in specific values for x and y. Well, how does so let's write that down here. So we know the gradient vector is, how do you calculate that? Isn't it the first partial, right? Times what? First partial with respect to x times what there? I, right? Plus the first partial with respect to y times j, correct? Now, but we calculated these partial derivatives a moment ago, right? What was f sub x? I had it circled up here, I think, right? Way up here. Oh, there it is, right? It's minus 8x. And while we're at it, what's f sub y? Minus 2y. If I can see it again here. Yeah, minus 2y. So we have here that this gradient vector is minus 8xi plus, I'm sorry, minus, right, 2yj, right? So that's the gradient vector at this arbitrary point that I've picked out here on this curve, xy. We're getting there, David. So let's take it slowly. All right. Now, I have to turn this though. I have to turn this vector. Or I don't have to turn it into, but I have to think of what's the slope of this vector. Okay. What is the slope of this vector? So how would you, if you want to give that vector a slope, vectors are lines, they really don't have slopes, right? But if we want to think of it as having a slope, if we want to think of that as being a line or a line segment, what would its slope be? Nope. No, no. You're thinking of slope on the surface, right? Elijah, you're thinking of slope on the surface, which is the magnitude of the gradient, okay? But I just want to think of the gradient itself as being a line. What's the slope of this line? See what I'm asking? So not what's the slope of the surface here, but just think of that as being a line in the XY plane. What is its slope? What's the rise over run here? Yeah. So what's the change in y over the change in x? Look at this. Look at that gradient vector formula there. What's the change in y? Isn't it minus 2y, right? And what's the change in x? Minus 8x, right? Okay. It's the coefficients of the I and the j that are going to that you can turn into slope. Yeah, I've done that several times already. Okay. But you're a little bit confused because you're looking at them in terms of variables here, right? If I said, oh, draw me the vector 4i plus 2j, right? What's 4i? Where's 4i plus, oh, maybe that's not it. How about 2i plus 1j? So where's 2i plus 1j here? So that would be maybe up here, right? There's the vector 2i plus 1j. And if I said, okay, what's the slope of that line? You would say what? Oh, it's 1/2, right? It's 1/2, right? Okay. Same thing here, right? Here's this vector. Its slope is just that the coefficient of the j divided by the coefficient of the I. Now, what's the significance of that slope? That slope is the slope of this curve. Now, David, how do you calculate the slope of a curve in 2 dimensions? What tells you that? Nope. Nope. Integral and derivative, same thing. Yeah, what gives you the slope of a curve? Not integration. Derivative, right? It's the derivative. Okay. So the derivative of this curve is this slope. Now, how do we write down derivative of a curve? Well, you could write f prime of x, but this curve is not a function, right? That curve is not a function. So I can't write f prime of x. I'm going to have to write the derivative of this curve using old-fashioned classical notation, and that would be dy over dx. There's a place where the classical notation is full. This curve is not a function, but you can still calculate its derivative, right? Okay. There's the classical notation. Oh, so what's the derivative equal to? It's got to be the slope, right? Oh, there it is. It's minus 2y over minus 8x. Oh, let's reduce that a little bit because the minuses divide out, right? And what's and the 2 over 4 will reduce, right? Oh, so you end up with this equation, dy over dx, the derivative is I over x. That kind of equation is called. It's a differential equation. So notice this, and this happens all the time in math and science. Don't know the curve, right? We're trying to figure out this curve. Don't know the curve. We don't know the formula for the curve, but we know the next best thing. So Isn't that the next best thing? Now, it's fine. But I, what? Yeah, we're gonna integrate. Okay, so we're going to integrate now. We're gonna find the anti. Okay, all right, look, now to do the antiderivative here, you're gonna have to do what's called separation of variables, right? Because I have to have dy's with y's and dx's with x's, otherwise I'm not gonna be able to integrate, okay, right? So let's see if we can achieve that. Can I get the y with the dy? Can I just divide both sides by y, right? Or multiply both sides by 1 over y, won't that do it? See, won't that wipe the y out here, and then the dy will be over here with the y, right? And I got to get the dx with the x. So how can I get the dx over to the other side? Multiply both sides by dx. So at the same time I'm dividing by y, I'll multiply both sides by dx. So what happens there when you do that? You get what? Dy over y is equal to what happens on this side? Am I doing that right? Yeah, dx over 4x. Now, just to make things a little, well, I really just so that I'm not dividing by 4 at the same time I'm dividing by x, let's multiply both sides of this thing by 4 so I can make this look a little bit nicer. So I have 4 times dy over y is equal to dx over x. Yeah, I like that a little bit better. And now we're ready to find the antiderivative. So how do I find antiderivative? Integrate, right. So now you're going to integrate. So we're going to integrate here. Now this is just a question of, can we do the integration? You can pull the 4 out, right? So you can get rid of the 4 and you're left with 4 times the integral of dy over y is equal to the integral of dx over x. And do you know how to integrate that? What? ln, right, there you go. That's the natural log actually of the absolute value of y, okay? And you have a 4 there. Don't forget the 4 is there. And when you integrate, of course, what comes along with the integration? For free? A constant, right. So you're going to have a constant on this side, and the same thing's going to happen on this side. So I'm going to have to label the constants because they may not be the same thing. So what's the integral here? I think it's natural log of, what's that? The absolute value of x, right? Plus another constant, okay? All right. Ooh, now we're cooking here, right? Let's see. One thing I'm going to do is let's pull this constant over to the left-hand side. And when you pull it to the left-hand side, you can combine these two constants, right? So that gives you just one single constant. So I don't have to give it a label now because I just have a single constant. And something else I can do at the same time. Remember, if you've got a coefficient on a natural log, what can you do with the coefficient? Can't you bring it up as exponent there, right? So you get natural log of y to the 4th power. I'm going to bring the 4 up, plus some constant is equal to the natural log of, there's the absolute value of x. Looking nice. Now, how do I get rid of those blasted natural logs? Really, in a way, this is it. See, I already have a form. This is the form, but you probably wouldn't formally write it. Okay, see, that's an equation just in x and y. Right? You have to figure out what the constant is. This is an equation in x and y. So you have Actually, already solved. So, yes. You know how to get rid of the natural logs? Yeah, you apply their inverse function, right? Which is raising both of those to the, or raising e to both of those powers, right? Now, remember, this is e to the natural log of absolute value of y to the fourth power plus the constant. This is also in the exponent now, right? This is easy though, because what does that turn out to be? Just, is that just absolute value of x? That's just absolute value of x. So we have absolute value of x now is equal to, so now you have e, but you can break this up because you can write this as e to this power times e to this power. See, here you have e to this sum. You can break that up as the product of two powers with base e. You know why that's the case? Because remember when you have powers with the same base, what exponents? Add them. This is really the same as e to the natural log of y power plus a constant, which is what we had. But when you raise e to a constant, guess what you get? You get a constant. So here you have another constant, then you can just call that c. So you don't have to write e to the c. So finally, here we are. We're ce to the, I'm sorry, c times, what's this? Yeah, but you raised e to that, right? So what happens to the, it would just be y to the fourth power. That's right. So you have c times absolute value of y to the fourth power is equal to the absolute value of x. But y to the fourth power is already positive, right? Because when you raise something to the fourth power, isn't it always positive? So you can drop the absolute values. So guess what? Just come up with this. Nice. Oh, so guess what your formula is for that curve? Well, it's something like x equal y to the fourth power. Now, we do need to figure out what this constant is, though. Do you know how to figure out what this constant is? I think you know one point on this curve, right? Because the crack starts at this point. So you know this point on the curve. So that tells you that if you take what? Y minus 3 and raise it to the fourth power times this constant, you're going to get what? 2, correct? And so what's the constant there then? Isn't that 2 over 81? Is 3 to the fourth power 81? I think so. So there finally is your, there's the final curve. 2 over 81 times y to the fourth power is equal to x. There's the formula for that curve. Oh, why did I drop the absolute value of x at this point? I could drop the absolute value around the y's, by the way, because again, when you take y to the fourth power, that's already positive. So you don't have to worry about absolute values. But the reason you can drop it here is we know that this crack is over on the right side of the x-axis, right? So we already know the x values are going to be positive. So, so just our visual intuition tells us. But the constant's not. So there's our, there it is. All right. Wow. That's fantastic. Okay. I mean, that's really using some high-powered logic there. That's using our knowledge of gradients and our knowledge of integration and other things there, right? To figure out what the equation for that curve is, or what the equation for that crack is. Okay. I like that problem. So I think there's kind of one similar to this in your homework, but it doesn't require you to solve the differential equation. I know some of you have solved differential equations like this before, but some of you, the logic is easy to follow, but need practice. Do this. necessary to help solve it. Okay. But it's just integration, right? Because it's just finding an antiderivative, right? Because that's the opposite of differentiation. All right, so now we're going to switch to something that's a little bit easier. So you're gonna like this, I think, and not find it hard. Once we get through the conceptual understanding of how things are working, you'll find it easy because the formulas at the end are. And this is another example in Calculus 3 of doing a lot of what appears to be high-powered mathematics and ending up with a beautiful formula that's very easy to use. So our problem here now is going to be finding formulas, equations for tangent planes. So you spend a lot of time in Calculus 1, right, finding formulas, equations for tangent lines to surface to curves. Here we want to find the equation for a tangent plane to a surface. So this is easy to imagine, but this picture. But here's a picture of what it is that we're trying to do, right? So you have some surface, right? You have some surface, some quadratic surface, right? But I don't know what this example, that particular surface is, and we identify a point on that surface. Right, we identify a point on that surface, so it has 3 points, right? And of course, you calculate the coordinates of that point by taking x and y coordinates, try to plug it into your function, and that's how you see. But you can imagine, right, that at this point on the surface, you can draw a plane, a flat plane, that touches that point on the surface, but doesn't slice through the surface. Okay? That's called. And that tangent plane sort of gives you, in a sense, a picture of what this surface looks like close to this point, right? Okay. Close to this point. Get very, very close to this point and blow up the surface very close to this point. It's going to appear to be a plane. That plane is the so-called tangent. Tangent plane touches the surface at that single point, but it normally doesn't slice through the surface. There are exceptions to it. Normally, tangent just hug the surface, right, and particular slice through the surface. So that's our goal here today, is we got a formula here for a function of 2 variables, right, and give it a point on that surface. How do we find tangent plane? Formula of tangent vector 2, right? So that's an important problem in Calculus 1, also an important problem in Calculus 3. This is a very important problem in the history of mathematics, though. Finding tangent lines to curves was a problem that was brought out by the ancient Greeks. Okay, they were not able to completely solve the problem. The problem was not solved. Actually, Newton's teacher, Newton had teacher 2, okay, and he was the one who actually was the first to sort of knew the solution to that problem, and taught that to Newton, of course. But Newton was the one who probably then put it in a more rigorous, gave a more rigorous solution to the problem than his teacher did. The ancient Greeks now knew how to find tangent lines to particular curves, but not just curves in general. Okay, so they knew how to find tangent lines to circles, for instance, or find tangent line to circle, but and other types of specialized types of curves they didn't know in general. As for any old curve and any old point, how do you tangent line that point, right? That didn't happen until the discovery of calculus by Newton and his teacher and other people at that time. All right, so but we are going to be able to do this really easily. All right, okay. So we're going to do it with an example, and the example is very instructive. So once you've seen the example, you'll sort of know what the scheme is for how to go through this. But let's stop for a minute. Okay, all right. So let's take a few minutes before we attack this and to take a break. So we'll come back here maybe at close to 1250, and then go through this example. And once you've seen this example, as I said, then you'll see this is really not all that difficult. Okay, given the knowledge that we already have. So let's pause here for a moment. All right, let's resume here and see how far we can make it into this example. I got it broken down into all these little tiny pieces, probably more than is necessary, but that's fine. That'll give us a chance to absorb what it is we're doing. So we're considering this function, z equals 1 minus 1/10 x squared plus 4y squared. The first question I asked there is, what type of quadratic surface is this? I don't know. You can look it up in your catalog there. All right. So did you find it? It's a paraboloid. Elliptic paraboloid. Certainly looks like an elliptic paraboloid. There's the picture of it, according to the book. All right. Okay. And what we're ultimately going to do here is try to discover the tangent plane at this point on the surface, 1, 1, and 1/2. So apparently we plug x equal 1 and y equal 1 into that formula that z equals 1/2. You'll see they've drawn the tangent plane here in pink on that surface, but that doesn't, to me, doesn't. Guess I'm not thinking of the surface properly. That tangent plane looks too steep. This particular, maybe that surface is a lot steeper. Right there, there's the tangent. Okay. So that plane is supposed to just touch that surface, that elliptic paraboloid, right at that point, right? But not actually paraboloid. To me, it looks like it's not supposed to. Right. Okay. So we're gonna try to find the formula that plane, right? Of course, we talked about formulas for planes, several weeks ago already, right? Or a few weeks ago, and so if we have enough information, right, we certainly know how to write down formulas for. We certainly know how to write down formulas for a plane. All right, so we'll trust Elijah's answer here. So elliptic paraboloid, apparently. And now we start with an easy question. What is the equation for the two-dimensional curve if we fix y to be equal to 1? So if you fix y to be equal to 1 on this elliptic paraboloid, that's right along this curve, right? Okay, so that's the curve that's going to be parallel to the x-axis, right? Because you're setting y to be 1. So I kind of drew that in here. I think that curve looks something like this. Of course, it's going to go through this point, right? Because this point contains the coordinate y equals 1. So let's see, what do we get? That's pretty easy, right? You just have to plug y equal 1 into your formula. So you get what? Z is equal to 1 minus 1/10. What is that? X squared plus 4, because y is going to be 1. So see, that's really easy, right? So remember, that's a two-dimensional curve, right? It only has two variables in it, z and x. So you can think of x as being the input variable here. You can think of this as being a function, actually, where x is the input variable, right? So the x can can vary from, well, I guess from minus infinity to infinity, right? And then of course you can calculate the z values. So that's how you're going up and down that curve, right? When you choose different values for x. So remember, this is a two-dimensional curve, right? Let's see what we want to know about that two-dimensional curve. I think we want to know something like, what is its slope at this point right here, correct? What is its slope? And then more than that, well, here's what we want to do. Let's find a 3D vector u that's parallel to this curve, at this point, right? And for some reason, it says choose u so that it has a positive x component, right? So when you find that vector, you want to investigate sure that it has a positive x component. All right, so I've drawn a picture there of the vector u. There's the vector u, right? Okay, because we want it to be parallel to this curve at this point. Okay, so how do you find now that vector u? That vector u, since it's got to be parallel to the curve, right? That means that vector u has to have something to do with what with respect to this curve. Yeah, it's got to have the same slope, right, as the curve, right, at this particular point. So we need to find what the slope of this curve is, right? Okay, we need to find out what the slope of this curve is at this particular point. Well, there's the curve, right? Notice that would be the same. We can express this in terms of partial derivatives, right? Because what we really want is the derivative of this surface, right, at this point but in what direction? Parallel to the x-axis, right? Parallel to the x-axis. Is that right? What I'd like to know is what's the slope of that surface parallel x-axis at that particular point, 1, 1, 2. So of course, how do you find that? One way, of course, would be to find this derivative, right? Okay, and plug in the right values for x. But I think I could just I think this part is kind of superfluous here, because I think we can also find this just using partial derivatives, right? Wouldn't this be the partial derivative with respect to x, right? At the point x equal 1, y equal 1, right? Isn't that the same thing? Isn't that what partial derivatives tell you, right? They tell you the slope of the surface parallel to a certain axis, right? This is parallel to x-axis. So what is that? What is that partial? What is that partial derivative? So in other words, what's f sub x of x y here? Can we think about that? Let's see. This becomes what? 0, right? This becomes not just going to be 0, right? When we take the derivative with respect to x, right? So we just have to differentiate the minus 1/10 times x squared. So don't you just bring the 2 down, right? And wouldn't that give you minus 1/5 times x? That minus 1/5 times x? Well, I'm sorry. This is, in general, this is minus 1/5 times x. And then when we evaluate it at 1, 1, correct? You just get what? Minus 1/5? So we want the slope of this, vector to be minus 1/5. So how can you write down that vector then? You want it to have a slope of minus 1/5, right? So remember, this is rise over run, correct? You're going to think of this as being rise over run, right? Each of the points by what points?
Oh,
No, you're making it, I think you're making it difficult, Elijah, right? Okay. See, I want to write down a vector that has this as its slope, right? So we just did that a moment ago, right? See, you're thinking of this as being rise over run, right? You're thinking of that fraction as being rise over run. So how can you write a vector that would have that rise over run, right? What now? 5, -1. So tell me that's got to have an I and J in it, right? So what would you put here? 5i minus J. Is that what you're thinking? That's a good attempt there, okay? But the thing you need to remember here, Robert, is we're not going in XY direction, right? The Y is fixed, right? So the Y component is not changing, right? The Y component is not changing in this vector, right? Okay, because the Y is fixed at 1, right? So you're really moving along the x-axis and along the z-axis, right? See, if you move from this point forward along this vector, the y is staying fixed, right? So the x is changing. This is fine, but it's not the z coordinate that's changing. So the j is what's the other? This is a three-dimensional vector. So what's the other component? K, right? Okay. Does that making sense to you guys? Y'all are always used to working with I's and J's, but this is going to be K. Okay. See, think of starting at this. Think of starting at this point, right, and moving along this vector. You would move 5 down the x-axis, right? But then you would move not in the y direction, but you would move down in the z direction, right? So you would move down 1 in the z direction. So this is it, right? The j is going to the y coordinate is going to stay fixed at 1. You're not moving here along the y-axis. So if you want to put the j component in there, you can. This is 5i plus 0j minus k. All right, if you want to write it like that. Now I'm going to write it though in a slightly different way. Let's divide everything by 5. So I'm going to have plus I minus 1/5 k. Okay. There's a reason I want to write it like that. Same thing, right? All right, now, so there's a vector that's parallel to this curve where y is fixed at 1, right? Okay. Now we're going to do the same thing, except now we're going to fix the x. Now we're going to fix the x. So I'm going to fix the x at 1. Of course, what's the equation here? As it turns out, we probably don't even need the equation. But what's the equation for this curve when x is fixed at 1? I already forgot what the curve is. So if you fix x at 1, you get what? 1 minus 1/10, 1 plus 4y squared. So you get z equal 1 minus 1/10, 1 minus 4y squared. But so, I mean, I think that's kind of, I mean, that's the equation for this curve that you can see. That's the equation for this curve that you can see right here. All right, where we fixed x to be, Now, I want the same thing though. I want to write a vector. I want the same thing now. I want to write a vector. I'm going to call it v now instead of u. That is parallel to this curve, or parallel to this curve, right? Okay, at this point. So how did I do that how did I do it when I wrote the vector u? What I have to do, I calculated the partial derivative. In this case, for u, I calculated with respect to x. For this vector v, we're going to calculate the partial with respect to y, all right? Because the vector v is going to be parallel to the y-axis. So let's see, what is that partial derivative with respect to y? Can we write that down? So what's f sub y x y? See if we can remember that. I have to scroll back up here. So if you take the partial with respect to y, this is a constant, right? So when you differentiate this, you just get 0, right? So it's going to be minus 1/10 times 4y squared. So when you bring the 2 down, that's something like minus 8/10 times y or something, right? So minus 8/10 times y, but I think you can reduce that. That's minus 4/5 times y. And now let's plug in our point. 1, 1. Of course, you just get what? Minus 4/5. And now, so that's the slope of that curve that we saw going left to right at this point. Or it's the slope of the surface in the direction of the y-axis, also at this point. Right, so there's the slope of that curve. Let's turn that into a vector. So what would that vector look like? Or what's a vector there that has that same slope? Remember, again, this is rise over run, but remember, the rise and the run in this case may not be quite what you're thinking they are, right? What's the run here? That's the y-axis, right? And the rise is, again, along the z-axis. So how do you turn that into a, how do you turn this into a vector? Wouldn't that be 4j minus 5k? See, if you go 4 along the y-axis from this point, if you go 4 along the y-axis, you're going to drop 5 on the z-axis. So this vector is 4j minus 5k. Let me, and I'm going to rewrite this one also. So let's change the v to be, instead of writing it like this, let's write this as j. Did I write that right? No. I have this backwards. I'm sorry. The run is along the y-axis, right? So this is 5, and this is minus 4. And now when I divide everything by 5, I get j minus 4/5 k. So I want to write my vector like this for a particular reason instead of like this. So there I've got them. Finally, at long last there are the two vectors that I'm going to use. Now, all right, so finally, all right, what are these two vectors good for? So why have I went to all the problem of finding two vectors that are parallel to the surface in these two directions, right? Well, I want you to notice those vectors are perpendicular to each other, right? And those vectors are perpendicular to each other, and they are going to be in the tangent plane. Those two vectors are going to be part of the plane, right? So those two vectors are in the tangent plane for this surface. Okay? And if you have two vectors in a plane, right, then how do you go about deriving? You take the cross product, that's right, okay, and what does that give you? It gives you the normal vector, and once you've got the normal vector, then you're done, right? Okay, then it's easy to write down the formula for the plane, right? So what we've done here is found two vectors that are going to be in tangent plane, okay? Since both of those vectors are parallel to curves, both of these vectors are parallel to the surface at this particular point. Both tangent is also parallel to the surface. So then just have to find the cross product, find it. Fine, let me see if I have a picture of that illustrated, maybe from the book's perspective, somewhere down here. Well, no, not really. Okay. There's just a picture of. There's just a picture of. Okay. But we have two vectors now in that tangent plane. Okay. And by finding cross product, find normal. And then we can write down. Now look, what was involved? Let's recall here quickly. What was involved in finding those two vectors? all we needed really was what? What did we really use to find those two vectors? This vector, that vector v, and this vector u. What did we really use to find those two vectors? I think it was only the partial derivatives, wasn't it? It was really just the partial derivatives, right? Okay, we found the partial derivative with respect to x, and we found the partial derivative with respect to y. That's really what we did in finding those vectors. Did you have?
Set by one, one.
No, it was, yeah, that was no reason. It was just a convenient example. There, yeah. We could have done the same with any point on the surface. It was just, I think, to make the calculations easy, to make the drawing easy. Yeah, there wasn't anything special about the x equal and y equal. This could have been any point on the surface. Yeah. All right, now, all right, so let's do that now. I think we can almost get through this now. So how do you find the normal vector? Y'all just told me we have to do what? We have to find the cross product, right? Now, the normal vector is in 3 dimensions, right? So remember to write your vectors down in 3 dimensions, right? These are vectors in 3 dimensions that we've discovered. These are not gradient vectors, okay? Gradient vectors exist in 2 dimensions. So let's see, what was that first vector? It was 1i something, right?
-1.
Yeah, 1i. So there's a 1 here, right? And a 0 here, and a -1/5 right there. Is that right? And then there's a 0 here, and a 1 here, and a -4/5 there. Yeah, okay. So now let's see. I forgot now how do we do this cross product here? Let's see. You'll kind of block this one off, right? And take the cross product in this direction, but that's so easy because that's 0. And so I get what? 1/5 I, is that right? Okay. And then what about J? You'll block this one out, right? And then you get what? 1 times this, 0 there, but you change the sign, right? So won't this become +4/5 J, right? And then what about for your K component? Block out this column, and so you get 1 minus 0. So that's 1, right? So did I do this correctly? Yeah, I did, right? Wow, that's pretty easy because what is this? Isn't that's the negative of fx 1, isn't it? Because it wasn't fx of 1, wasn't that positive, right? And what's this? This is minus fy 1, right? Because the partial with respect to x at 1, was -1/5. The partial with respect to y at 1, was -4/5. So look at what comes out. These are just these things just come out from the partial derivatives. All right, so there it is. There's the normal vector. So what's the equation for that tangent plane? Wow, I think it's so easy, right? So what do you do with the normal vector? It's the coefficients, right? So you would have 1/5 times x minus 1, right? Because this is the coordinate of a point that it goes through, isn't that right? Plus 4/5 times y minus 1, right? And then, and here just 1 times, because this coefficient is 1, z minus the z coordinate of this point, which is 1/2. And remember, all of that's equal to 0. Oh, wow. Okay. That was, that came out fast. Oh, so what was involved here? Actually, nothing. You don't even have to take the cross product, I don't think, because what did this coefficient turn out to be? Related to, at least. So what was this number really? It was the partial derivative with respect to x, right? Where did this number come from? It's just the partial derivative with respect to y, right? This is just 1. Okay, that just came out to be 1. That's the formula. Oh, okay. So there is the formula summarized here. It's slightly different form, okay, because we've changed the signs, all right? But here it is, all right? In this formula, they're going to use the negative of the cross product as the normal vector. The negative of the cross product would also be a normal vector, right? So they use that just to make the signs easier here, all right? So there's your formula for tangent plane. It's just first partial with respect to x, x minus x0. First partial with respect to y, y minus y0 times, and then this just turns out to be 1, z minus z0. But notice they switched the signs here. So these two are positive. This one. There's the oh, which is what we see, except we use the negative here as the normal vector. They changed the signs to make the signs easier. This leading signs. Awesome. Okay, all right. So, well, we made it through that example. So we're going to start next time with, we'll apply this. I'll let y'all do it once here in class, okay, with a different surface next time. All right, so we're out of time. We ran over here. So let's stop. I forgot to roll. So sign that quickly when you leave. And I'll see you guys on Wednesday. Don't forget your